The mathematics of two-slit interference. The geometry of a two-slit experimental setup is as follows. I have my two slits right here. I have my screen in the thick black line, and you'll see here in the middle there's a dashed line that's called the central line. The two slit openings are defined by little d. Then big D is the distance from the two slits to the screen where we observe the fringe locations. And then measured from the central line is y of m, and y of m is the location of the fringe. And then finally there's this theta of m, which is the angular location of the fringe, measured of course relative to the central line. To mathematically derive the equations for two-slit interference, there are two important triangles to focus on. So what you see here is that I've labeled two triangles. The first triangle that we'll focus on is 1, 2, 3. The second triangle that we're going to focus on is ABP. So let's start with 1, 2, 3. So I've now added the screen distance capital D. I've added the slit separation. And this light blue line is a perpendicular bisector. Now, if little d is much, much smaller than capital D, then I could make this angle approximation. That this angle here is approximately equal to this angle there. What this means then, if I look at this part of the ray, R1, and then from the light blue to the point P, that part of R2, those two are congruent. So then that means here that this little extra piece is delta R. So now I have an equation to solve for the path difference delta R. So focusing on triangle 1, 2, 3, all I did here was flip it so it's easier to actually solve for. I could then solve for dr. So delta R over d is in sine of theta, so the path difference is d sine theta. Next, I'm going to go to triangle ABP. What you're seeing here is I removed the blue line here and I've added y of m. So it's clear that this triangle has a side of y of m and a length here of d. So if I solve for this triangle, it looks something like this. So I could solve for this length y of m, the location of the fringe, in terms of theta and big D. What I end up getting is that y of m is equal to big D times tan of theta. In summary, we have two equations. We have delta R, which is d sine theta, and that's the path difference between two waves. We just spent a whole bunch of time on path difference and how they're related to wavelength and fringe number. And then I have the fringe location, which is d tan of theta, which tell us the location of the fringe on the screen. There are two possible cases: no small angle versus small angle approximation. Case 1, no small angle approximation. If this is the case, then we have to solve the delta R equation to get theta, and then we plug in theta into the fringe equation location. So I have these two equations that I got to solve for. Case 2 is small angle approximation. What you find here is for a small angle is that the slit separation is much, much smaller than big D. Then little d is much, much smaller than big D. And a small angle approximation can be applied to sine theta and tangent theta functions. But in two-slit interference, this is always the case. Because of this, I want to derive some other relationships that really help us intuitively understand what's going on. From a Taylor expansion, I could look at sine theta, and I could see that for small theta values, only the first term matters, and for tangent theta, only the first term matters. So you could see that sine of theta and tangent of theta are the same. Is a small angle approximation implies that sin of theta is approximately equal to tan of theta, which is equal to theta. From the two-slit interference equations, I could then write delta r as d theta of m. Y of m is approximately d theta of m. That means that I can eliminate theta of m from both of these equations. So y of m is the fringe location on a screen, which is equal to capital D delta r divided by little d. Now I want to mathematically analyze this equation and its details. The fringe location. There's two ways to locate a fringe, either by calculating y of m or theta of m. However, it's more common to use y of m. So now I want to look at bright and dark fringes, and I start with the path difference. We know that the path difference is mc lambda for constructive and md plus 1/2 lambda for destructive, where mc and md is equal to 0 plus or minus 1 plus or minus 2. Remember, plus means up the screen, minus means down the screen. The locations of constructive interference fringes is given by y of m, big D delta r over little d. But for constructive interference, we know that it has to be, I have to replace delta r by mc lambda. Therefore, the location of bright fringes is given by mc lambda big D divided by little d. The locations of destructive interference fringes follow the same process. So y of m of dark fringes differs by md plus 1/2 instead of mc, but it's the exact same equation. We see that in both fringe location equations, y of m depends on three parameters: the wavelength, the slit separation, and the screen distance. The focus is going to be on the fringe separation distance delta y of m for constructive interference. In other words, delta y of m is the change in fringe number times the wavelength screen distance divided by the slit separation. And the way I'm going to do that is I'm going to use a applet. So the interference applet comes from the textbook from Halliday, Resnick, and Walker. The first thing I want to look at is I want to look at what happens to the fringe separation. By looking at this equation, I see that the fringe separation is proportional to the wavelength. In other words, delta y of m is proportional to lambda. Mathematically, we see that if we have longer wavelengths, therefore I should have larger fringe separations. If I have shorter wavelengths, I should have smaller fringe separations. Why is this true physically? If the wavelengths are longer, there is less locations where they will overlap and produce interference patterns. Therefore, the fringe separation increases. On the other hand, if the wavelengths are shorter, there are more locations. And if there are more locations, then the separation has to decrease. Let's go see this in the applet. So in this applet, what you're seeing here is that I have the two-slit mode. Here's my interference pattern, and you'll note here that these intensities are not all the same. I'll talk about this later on. But what you find here is four things. I have wavelength, slit width, which is something that we won't really focus on right now. I have slit to screen distance, so this is the screen distance, and this is the slit separation, little d. So this is little d, big D, and then wavelength. This we won't talk about. Look at the separation of the fringes. So it's this guy. So if I increase the wavelength, the separations should get large. And you could see that the separations have increased as expected. If I decrease the wavelength, the fringes should get closer together, which they do. So I have two cases of longer wavelengths, the fringe separating, shorter waves, the fringe get closer together. So in summary, if I have longer waves, there's an increase in the fringe separation. If I have shorter waves, there's a decrease in the fringe separation. Mathematically, I say I have a big y sub m when I have longer waves, everything else being the same. On the other hand, I have a small delta y sub m when I have a small lambda. The second variable is the slit separation. Mathematically, we see that the fringe separation is proportional to 1 over the slit separation, which means that delta y of m is proportional to 1 over little d. Question: what happens to the fringe separations as little d changes? Mathematically, if I have a smaller slit separation, then I should have larger fringe separation. Or if my two slits are farther apart, I'm going to have a smaller fringe separation. Question: why is this physically true? If the slits are closer together, there are less spots for the waves to overlap, while slits farther apart allow more overlapping, where the fringe separations are then going to get closer together. Let's go look at this at the applet. So once again, I'm not touching the slit width. The wavelength I'm going to fix, the screen distance I'm going to fix, it's only the slit separation. So if I increase the slit separation, what happens to the fringes? So they get farther apart, there's more locations for them to interfere, so therefore I get more interference patterns. Therefore, the slit separation has to decrease. If I decrease the slit separation, there's less spots for them to interfere. Therefore, the fringes have to spread out more. Let's run through this one more time. As I increase, more places to interfere, delta y gets smaller. As I decrease it, less places to interfere, delta y must get bigger. In summary, if I have a smaller little d, then I'm going to get a larger delta y. In other words, if the slits are close together, then the fringe separation is going to get larger. Mathematically, we see that if I have a smaller d in the denominator, I'm going to get a bigger delta y. On the other hand, if I have a larger slit separation, that means more places to interfere, then I'm going to get a smaller delta y. Mathematically, I have a big little d in the denominator, therefore a smaller delta y. The last of the variables is the screen distance. The fringe separation is directly proportional to the screen distance. In other words, delta y of m is proportional to big D. Question: what happens to the fringe separations as the screen distance changes? Well, mathematically, if they're directly proportional, if I have a smaller screen distance, I have to have smaller fringe separations. If the screen distance is larger or farther away, then I'm going to get bigger fringe separations. Question: why is this true physically? If the screen distance is closer, the overlapping of the waves do not get a chance to spread out as much, so the fringes are closer together. If the screen is farther, they spread out more, and therefore the fringes are farther apart. Let's go look at this in the applet. So for this simulation run, the wavelength is fixed, the slit separation is fixed, only the screen distance is what's being changed here. So what you want to pay attention to is the fringe separation. Now, if I make the screen distance smaller, I should see smaller fringe separations. So as I decrease this thing, note that the fringes have gotten closer together. If I increase the screen distance, they should get farther apart. And you could see that they're getting farther apart. So decreasing it, fringes get closer. Increasing it, fringe distance gets farther. In summary, if I have a smaller d, then I'm going to get a smaller delta y. Mathematically here, you could see that if I have smaller d, it's directly proportional to the fringe separation being smaller. If I have a larger d, then they spread out more, so I get a bigger delta y. So you could see that a bigger d gives me a bigger delta y.